about applications. Okay, this one is how to use exponentials and logarithms in applications, and here we talk about what we call logarithmic models. Okay, so let me explain what this is. So the way this is, we're gonna do this is I'm gonna write down a definition here. Okay, so in this page I'm gonna be writing some definitions, but I'm gonna be coming back and forth as we go along, and then we're gonna do several examples. We're gonna do some examples on exponential growth, some word problems. Then we're gonna do some examples on what we call exponential decay. Mainly, I wanna discuss here this idea of carbon dating. You know, this is what the archaeologists use when you find remains. You know, if you find some object or some bones, some remains that have been buried for some time, and sometimes they say, oh, these bones are, I don't know, 2,000 years old, something like that. How do they figure this out? Okay, this is called carbon dating. We're gonna discuss how to do this, and also another application using what is called Newton's law of cooling. Okay, like if you bake a pizza and you know, you take it out of the oven, maybe it's 500 degrees, it's super hot. How long do you need to wait until it reaches a temperature that you can eat, like 70 degrees or less, something like that? I don't know. Okay, so this is Newton's law of cooling. We discuss some of these applications. All of these, they are under the umbrella of exponential and logarithmic models. All right, so let's see. So right now here, I'm gonna write something very general, and then we're gonna look at the examples. So here's a definition. What do we mean by exponential growth or decay? So suppose that you have a quantity, let's call it y of t. Usually here, t, the variable t is used because, you know, it represents time. And in this application, usually time is what's changing. Okay? It's your free variable. And you are observing what happens to this particular quantity over time. All right, so a quantity y of t is said to grow or decay exponentially with respect to t if it satisfies the following formula. If y of t has the form y sub 0 e to the kt, where y0 and k are constant. Y0 and k are constant. Okay, so that's what it means for a quantity to grow or decay exponentially. So how do we know whether we have grow or decay? Well, the constant k will tell you this. Okay, so if the constant k is positive, then the model represents exponential growth. Okay, and how will it look like? So in that case, see, notice that in this case, it's going to be an exponential function, and because k is positive, that means that the base is bigger than 0. Okay, so the initial value is y0. That's what this guy represents. That's the initial value, because when you plug in t equals to 0, you're going to have e to the 0, which is 1. Okay, so that's your initial value, and then it's exponential growth. So it's going to look like this, right? Usually, of course, there is this other part of the exponential, but we don't write it. Why don't we write this? To be of t. Because remember, here t represents time, and talking about negative time usually doesn't make sense. Okay, so that's why we always consider what happens at t equals 0 and after that. So we only graph usually this piece. In applications, we don't care what happens when t is negative most of the time. So what we can see here is that as t approaches infinity, so as time grows, the quantity grows. Okay. All right. So that's exponential growth. And how do we know that we have exponential decay? Well, the k tells you that, and if k is negative, then the model represents exponential decay. And the reason is, for example, imagine that you have y equals e to the negative 2t. This is the same thing as saying e to the negative 2 to the t, which is 1 over e squared to the t. So this is an exponential with base less than 1, so it decays. it decreases. Okay, so that's why if k is negative, you get decay instead of growth. Right, erase this. Doesn't get confused. So if k is less than 0, then the model represents exponential decay. And how does it look like? Very similar. It's just that you have the decreasing version. So again, you have the initial quantity, keep writing x, which is y0. Let's put it here. And now, as time passes, the model decays. Okay. So once again, we have this piece right here also, but we usually don't write it because in applications, time is always positive. That's the only thing that we are interested in. Okay, so it looks like this. And what's the end behavior? So as time grows, as time passes, what happens to the quantity? It approaches 0. Okay, that's what gives you decay. The first one is growth because as time increases, the quantity increases. The second one is decay because as time increases, the quantity decreases. Now, this number k has a name, so we usually refer to it in absolute value. So the absolute value of k is called the growth or decay constant. It's called the growth, and the reason why we look at the absolute value is because the name already tells you whether it's positive or negative. So if we say the growth constant, we already know that k is positive. If we say decay, we already know that it's negative. Okay? It's called the growth or decay constant or rate. Sometimes we say the growth rate or the decay rate. So remember, growth represents positive k, decay represents a negative k. All right, questions? I mean, well, I just wrote a definition. I really haven't done anything fancy. So, do you understand what I just wrote? Okay, so let us. Yes, Maria.
Oh, in the book it says that if k is between 0 and 1, it has exponential decay. So it is like
K or
it
the
always has to
base?
be
You mean
oh
K or the base?
the base.
Then exactly. So the base is between 0 and 1. That will happen when k is negative. So again, like I said, look at the general formula, right? E to the kt. What happens if, so the y0 is really not important, that's just the initial quantity. So what happens if k is negative? That was the little example that I was writing. Mind that you have a negative 2. This is really 1 over e squared to the t. So this right here will be base between 0 and 1, right? Because this is less than 1. That's why you get decay.
Oh, okay. Got it. Thank you.
Yeah, that negative k is the one that makes the base less than 1. So in some places, you have to be careful when you're doing the homework. You need to see because there are some books. I don't recall exactly. I have to look at the book again to see what was the convention they're making in the book. But what I'm trying to say here is some places they call the constant, the growth constant or the decay constant. Sometimes they include the sign. But that's kind of a redundancy because if you say growth constant, it's already understood that it's positive. So you just tell the absolute value. You say decay, that already means that it's negative. For example, in this language that I'm defining, we will say the decay constant is 2. So imagine that you have E, let's see, because you have to identify, imagine that you have this function, okay? I will say the decay rate is 2. So this function decays with a constant rate of 2. When I say decay, I am already implying that it's going to be negative. But there are some places in which k, the constant rate of decay is included with the negative, and they will write negatives, and they will say negative 2. Okay? So just keep that in mind. It's just a matter of language. Okay? So the way I'm going to be speaking is when I say the growth constant, I mean it's going to be a positive number, and then I'll just tell you a number. If I say the decay constant is 3, I mean really negative 3, because the word decay already tells me the constant is negative. Okay, so it should not matter too much. In fact, the reason why I'm pointing that out is because notice that in this definition, I did not include the negative. You see, it's e to the kt, and the sign of k tells me everything. There are some places in which you will see this. Okay, in which you're gonna see this for decay, and then for growth they will write this. But when they write this for growth, they will specify k has to be positive, and then for decay they will write it like this with a positive k all the time. So in some places, k is always positive, and then they manually put the minus in the formula to include whether you have decay or not. I'm not doing that, okay? I'm just putting the general formula, which is y0 e to the kt. And when you look at k, if it's positive, you know it's growth. If it's negative, you know it's decay. But this way, instead of having two separate formulas, we only have one, okay? So just keep that in mind. And again, you know, this is just a different way of looking at it, but it's exactly the same thing. Okay, it's just that I would rather have one formula than having two different formulas. Okay, question. Now we're going to do examples. Question. Right, so let's see. Let's take a look at this example of growth, and then we talk about decay a little bit more. Okay, so on January 1st, 2000, the population of California was approximately 34 million. So this is an example of population growth. On January 1st, 2010, the population was 37.3 million. Okay, asking three parts here. So part A, write a function of the form P of t equals P0 e to the kt to represent the population of California in millions 3 years after January 1st, 2000. This is important. Remember, we already did one example similar to this, and you know, it's kind of important to have this in mind. Okay, so t years after January 1st, that's what P of t represents, and round k to 5 decimal places. So remember, to find this formula, at some point we need to figure out what's P0. What we actually need to find is P0 and K, right? So to find this, once you find K, usually this is going to be an irrational number. We're going to write the exact formula, but then we're going to also give it rounded to 5 decimal places, the K, because it's more friendly to look at that way. That's part A. Then part B says use the function in part A to predict the population on January 1st, 2018. And then we round to 1 decimal place. And finally, part C, use a function from part A to determine the year during which the population of California will be twice the value from the year 2000. In other words, when will the population double? Okay, of course, these models that we are doing here are not really realistic because, you know, it's not taking into account that people die and, you know, people may move to another state and, you know, spaces and all that business. So the type of model that takes more of this into account is called a logistic model. But this one, notice that this one, if you let time goes to infinity, it grows to infinity, but we know it's not true. You cannot have infinitely many people living in California, okay? But for low values of t, this model is close to what the logistic model would tell you. Okay, anyways, let's go ahead and let's do this example. So the first thing that we should do is write down the information that we're given. Okay? So solution. Let's see. We know that we have a function p of t, and what does this represent? This is the population of California 3 years after. This is very important. After January 1st, 2000. Okay, let's keep that in mind. This is 3 years after January 1st, 2000. Okay, so when we read the problem, the very first sentence, what does that mean? What information does that give us? When they say on January 1st of 2000, the population was approximately 34 million. What does that mean about the function? And this, remember, is in millions. So this population is given in millions. So what does that mean? What would be t in that case? So what is given to us? So what is t? T is equal to 0. Very good. So this is telling us that if t is equal to 0, so p of 0 equals 34. Does everyone understand this? All right. How about the second sentence? What's the second sentence telling us? What is the second sentence telling us? They say on January 1st, 2010, the population was 37.3 million. T equals 10. Very good. So P of 10 equals 37.3. Okay. Now with this information, we need to go ahead and figure out the model. Notice that this problem is similar to what we did earlier, but earlier we didn't have this specific form. We were working with A times B to the T. Remember that? And then you were given 2 points on the graph of the exponential, and then find the equation. Here we're going to do the same thing, but instead of A times B to the T, we have a more specific form. We have, you can think of P0 as being your A, that one doesn't change. But then instead of B to the T, we have E to the KT. So if you want, the B here is E to the K, right? This is your B. If you want to make the analogy from the examples that we were doing earlier, like maybe, I don't know, what is it? 4 lectures ago, something like that. Okay, so let's see, let's do this. So as you know, what does P0 represents? P0 represents the initial population. That's what the subscript 0 represents. In science, when you write a subscript 0, it means initial quantity. Like in physics, in chemistry, usually we write this a lot. So P0 represents the initial population because that's what you get when you plug in 0. So this right here immediately tells you that P0 equals 34. So you understand this? You notice, so again, what I'm saying is, if you plug in 0 into P, what do we get? We get P0 times e to the k times 0, plus P0 times e to the 0, which is 1. Okay? So P of 0 is the same thing as P subscript 0. That's what the subscript 0 means. It's the value of the function as 0. So the initial population is 34. So that means that so far, the formula is looking like this. 34 times e to the kt. Okay? And we have population growth, so we are expecting k to be positive. But let the calculations tell us this. So now the question is, what is k? Right? We're trying to do part A. So we are trying to figure out part A here. So let us try to find k, and for this we're going to use the next point. Okay? So we know that P of 10 on one hand is going to be equal to 34 e to the 10k. Now on the other hand, P of 10 equals 37.3. So we have 37.3 equals this quantity, and then our job is to solve for k. Now here we need to use logarithms, right? So to solve for k, what do we get? And right here, e to the 10k. This is going to be 37.3 over 34. We can write this using logarithms. So that means that 10k equals ln of 37.3 over 34. So finally, k is going to be ln of this divided by 10. Okay, this is the exact value. Okay, and like the problem said, let's approximate this to 5 decimal places. So what do we get? 37.3 divided by 34, ln of that, and then divided by 10. Okay, so we get about 0.00926. Okay, that's the approximation. So what is the model? I'm going to write down the exact model. It would be 34 times e to the ln of 37.3, 34 over 10 t as the exact model. But then if you want an approximation of it, that would be 34 e to the 0.0926 t. Okay, questions about part A? Questions? The formula is P0 e to the kt. So remember, guys, you can these notes they are also available online. So if you get behind writing this, it's okay. Just make sure that you can follow what I'm doing, because then you can fill in the gaps. Okay. All right. Okay. So any questions? All right. So let's see. Let's take a look at part B now. Let's see. Let's go to part B. What does part B say? So now we have a formula. Okay. So we have a formula that all what it does is it tells you the population of California, or an approximation of the population 3 years after January 1st, 2000. So all you have to do is plug in a year, a value for t, and it will tell you the population. Let's see, part B. Use the function in part A to predict the population in 2018, January 1st, 2018, round to one decimal place. So how do we do this? What do we need to do to answer part B? Very good. We already have a formula for t, so all we have to do is plug in a t, right? Because 2018, that's just P of 18. All right, that's really what they are asking. So straightforward, so let's do it. So part B, all we have to do is figure out what's P of 18. So this is gonna be 34 times E. Okay, I'm gonna work with the simplified model. So this times 18. So let's see, what do we get? Let me store in memory here, the exact value. Okay, so I'm gonna work with the sub value in my calculator because I did not erase that. Okay, but you can work with the approximation as well if you like, since the problem is telling you to do so. Okay, so multiply by 18, then we do to the power, and finally we do times 34. Okay, so it looks like we get 40.169, etc. So it says to round to one decimal place, so I'm gonna put 40.2. And the reason is because the problem itself is gave you a data rounding to one decimal place, right? When they say 37.3, so that's why here we're rounding to one place as well. So 40.2, and remember this is in millions, so this represents millions, okay? That's 40.2, and remember that means that in January 1st of 2018, the population is about 40.2 million. The population California was about 40.2 millions. Okay, questions on part B? Okay, perfect. All right, so let's see. Let's take a look at part C. It says use a function from part A to determine the year during which the population of California will be twice the value from the year 2000. All right, so what do we do here? How do we answer this question? Exactly, so twice from the population from the year 2000 2000, what they're really asking is when will the population double, right? So initial population times 2. Very good. So when will the population double? So notice that in this case, let me write this down. So in part C, so to answer the question in part C, what is it that we need to do? So we need to find T such that, okay, such that P of T equals 2 times the initial population. In other words, 2 times P of 0. This T, this number has a name. This is called the doubling time. Okay, so such a T, the T that we're looking for, such a T is called doubling time. And it should be clear what the definition is. What the definition of doubling time is the time that it takes for a certain quantity to double itself. Okay? Given a model, the time that it takes for the quantity to double itself is called the doubling time. All right. So having said this, then let's go ahead and let's find it once again. It's clear what the condition is. We want to solve this equation, right? P of T equals 2 times PC. So let's see. So when is it that the population will be twice the original amount? So by the way, notice that we can actually find the doubling time without even knowing, okay? Without even knowing what the initial amount is, because what do we know about the population? The population equals to P0 times e to the kt. And the question is, when is this equal twice the original amount? And notice that actually the original amounts cancel. So the doubling time is independent on the initial amount. Okay, that is not related to initial amount, it's related to the rate at which your quantity is growing. Depending on K, the K is the one that tells you what the doubling time is. The initial amount is irrelevant here. Okay, this is a very important observation. Okay, anyways, so I'm doing it like this so we can get a formula, right? So notice that I did this for a general model. We have e to the kt is equal to 2. So this means that kt equals ln of 2. So t equals ln of 2 divided by k. This right here is the formula for the doubling time of an exponential model, okay? Of an exponential growth model. So this is the doubling time formula. Doubling time formula for exponential growth. Okay, but you don't have to memorize it because it's very easy to come up with this formula. Doubling time means how long it takes for the initial quantity to double itself, and you can calculate it this way. You set the function equals to twice the original quantity. It cancels out, so t is just ln of 2 divided by k, right? Notice now that with this, we can then figure out the rate of change of the quantity, so the rate at which the quantity is growing, if you know the doubling time. Because this means then that k is going to be ln of 2 over t. Okay? But in this case, t is the doubling time. So if you know that a quantity is doubling, that the quantity, if you know the time that it takes for a quantity to double itself, then you can do ln divided by that, and you will know the rate of growth of that quantity. For example, there are typical problems that say population of bacteria doubles every 2 hours. Okay, and then find an exponential, and let's say that you have an initial amount of 30 bacteria. What would be an exponential model that tells you how many bacteria there are 3 hours after whenever you mention it from the first time? You know that it doubles after 2 hours. Every 2 hours it doubles, so that means the doubling time is 2 hours. And so k would be ln of 2 over 2. You can immediately say that then your exponential model of the bacteria will be P of T equals the initial amount of bacteria, whatever it is. Let's say it was 30 bacteria, t to the ln of 2 over 2t. Okay? Because k would be ln of 2 over 2. Anyways, that's just how you can use these concepts, okay, to quickly come up with formulas like that. So once again, the t here is not whatever you want. That one is the doubling time, the one that is in the blue box. Okay, so applying these to our problem, so we are looking for the doubling time, and we know that this is ln of 2 divided by k. We already have k, so we figured out k, it was about 0.00926. So let's calculate the doubling time. So this guy, repeat times ln of 2. So we have about 74.83. Okay. And remember, this is in years because t is in years. So 74.83 years. So when will the population double? So when will the population double? It will be around the year 2074. Okay? So the population will double around 2074, around the year 2074. Because it's not quite 2075 because it's less than 75 years, right? So you can also estimate more or less the month in which this will happen, but we're not getting there. Right? Okay, anyways, questions? Okay, so do you guys understand this concept of doubling time? And that right there is the formula to calculate. Okay, but you know, don't memorize it. There will be a lot of other stuff that you need to memorize in this class. So for this kind of things, don't memorize this because as you can see, it's very easy to obtain that formula. If you understand what doubling time is, then you can easily obtain the formula. Doubling time means the time it takes to double the amount to double. So you write down the first equation, P of t equals 2 times P0, and then you can figure out t very easily. You can see it depends on k, right? But, you know, it's good to know it because then you can answer some questions very quickly if you know them. But it's not really necessary to memorize that. Okay, all right, so that's an example of exponential growth. So let's go ahead then and keep looking at other examples. For example, let's do exponential decay. And for that, I'm going to come back and keep writing a little bit more definitions. Okay, so to be able to talk about exponential decay, let me first give you some more definition. So what do we mean by radioactive decay? So let me say here, so radioactive decay. So radioactive decay. And this is basically when a quantity, so when an amount decays over time, if you don't do anything to it, you just let it sit, and then time starts to go by, the years, and then the amount of the quantity starts to decay. Okay, compose, like it becomes other materials. That's what we mean by radioactive decay. So the amount A of radioactive material present at time t is given by the following formula. Again, it obeys an exponential model. It's given by, and again, you're going to be able to justify these formulas. Those of you that are going to study actually differential equations, really with calculus 2, you will be able to answer, figure out these formulas on your own, like see why the models are the way they are. But really, in differential equation is when you're going to come back to these ideas again. So those of you that are going to take a differential equation, these type of problems are going to come back. Okay. All right. So the amount A of radioactive material present at time t is given by the following formula. So it would be A of t equals A0 times e to the kt. Now again, this is decay, so it is understood that in this model, k is negative. Okay? You may see in some places that they will write this, they will manually put the negative, because then their k is positive. Okay, remember, in our case, I'm just writing k in general, and letting k tell me whether we have growth or decay. All right. So in this case, when I write A0 e to the kt, to have radioactive decay, you need to have a negative k. So that means that we're going to have exponential decay. And of course, A0 here was A0. A0 represents the initial amount of the material. Okay? Like, I don't know, amount of grams and stuff like that. Okay? Initial amount. Right. So that's what radioactive decay is. And I'm gonna come back when all the notions start to pop up, and then we're gonna discuss it. In fact, since I know that that's gonna pop up, let me do it right away. We can just focus on the example. Remember that in the case of growth, we had that notion of doubling time, okay? Which is the idea of how long it takes for a quantity to double itself when a quantity is growing at a certain rate. Well, when a quantity is decaying at a certain rate, we have a similar idea. At this time, instead of calling doubling time, it's called the half-life. Okay? So every radioactive quantity, every radioactive material, it has a half-life, and there are tables that chemists and physicists have, approximated what the half-life is of those quantities. Okay? And what's the definition of half-life? Well, half-life, like the name suggests, is the time it takes for the quantity to reduce by a half. Okay, the time it takes for half of the radioactive substance to decay and turn into something else. I don't want to say disappear, because as you know, things do not disappear; they just change into another state or another material. Okay. Anyways, let me write it down. So that's why I don't want to use the word disappear. Okay, so half-life. So what do we mean by half-life? This is the time it takes for half of the radioactive material to decay. Time it takes for half of the radioactive material to decay, or radioactive substance to decay. So using this definition, let us try, let us try to come up with a formula. Right. So let me actually, the notation that we had here, for doubling time, so that we don't get confused ourselves, let's call it dt. So the t here is doubling time, so I'm going to put here dt. Okay, dt. So let me put here dt. That's for doubling time. Okay, so such a t is called doubling time, and then t sub dt. Okay. So with that, now we're going to use a similar notation for half-life. I'm going to call it THL. Okay. So i.e. THL, what is this? This is the half-life. If we call this half-life, then what does that mean about the quantity itself? So if we plug in THL into the function A of t, right? So we have A of t is equal to A0 times e to the kt, because this is the half-life, this is the amount of time it takes for the original quantity, the initial quantity, to decay by 1/2. So this better be equal to 1/2 the original amount. Remember, in the doubling time, It was the time that it took to double itself, so it's equal to 2 times the initial amount. This time is 1/2 the initial amount. Okay, so with this relation, once again, we can come up with a formula. And as you are about to see, the initial amount is irrelevant. This half-life depends entirely on the rate, once again. So let's see, what is this? This is A0 e to the kt is going to be equal to 1/2 A0. So the A0s are gone. So we have e to the kt, right, HL, because now we have half-life, equals to 1/2. So kt equals ln of 1/2. So we have that the time, the half-life is going to be given by ln of 1/2 divided by k, right? And if you want something similar to what we had earlier, notice that we can actually write ln of 1/2. Formula right here. So this is the half-life formula. So formula for half-life. So remember, don't forget that here k is negative, okay? So you can also write this as ln of 2 to a negative 1 over k, which is minus ln of 2 over k, right? So in some places you may see the formula written like this, because now this is very similar to the doubling time formula that was ln of 2 over k. It's just that the half-life formula is minus ln of 2 over k. And this is consistent because remember, time is supposed to be negative, it's supposed to be positive, and we are seeing a negative in this formula, but recall that k is negative. So the negative of the k, together with the negative that is popping up here, is making the quantity positive, which then is consistent with the fact that time is positive. Okay, so this is a formula for half-life, and similarly, if you know the half-life of an object or a radioactive quantity, then you also know the constant, the rate at which it decays, as given by ln of 1/2 over the half-life, which you can also write it as minus ln of 2 over the half-life. Okay. Questions? The way we obtained these formulas, it was very similar to the doubling time. Okay, so once again, you should not be memorizing these formulas. But what is really important is the definition. If you understand what the half-life is, you can always recover this formula that we just came up with. So that's the reason why I'm showing you this. All right, are you okay with this? Okay, so now that we know this, let's go ahead and let's do some. All right, so carbon 14. So like I said, there are some materials out there that we know that they have life, okay? The carbon 14 is an example of this. So carbon 14 is a radioactive material and it has a half-life of 5,730 years. Okay, these are approximations, okay? And you may find tables with maybe it says 5730, another one may say 5731 or 32. It's an approximation. 5,730 years, write a model of the form Q of t equals Q0 e to a negative kt. So notice that here, the negative is already being included. Okay, keep this in mind. To represent the amount Q of t of carbon 14 remaining after t years if no additional carbon is invested. In other words, if you just let it sit there and nothing else happens to that substance that has carbon 14. Okay. All right, so let's see, let's do this. So solution, let's see, the first one is let's find the model if we know the half-life. So what do we know? We know that the half-life is going to be 5,730. And then we have the model, which is Q of t equals Q0 e to the negative kt. Again, if you wanted to, you could use the formula that we developed to figure out this quantity, including the negative. Okay? Because remember, the formula will give you the negative. So you can use this to figure out k. the formula we just developed, or just use the notion of half-life. That's what I'm gonna do. Okay, I don't like memorizing formulas. So sometimes you have to memorize, but you should keep your memorization to the minimum. Because when you memorize something, that means you can forget it. Now, when you understand something, it's harder to forget. Okay, understanding is a different story. Okay, anyways, we want to figure this out, and all we are given is the half-life, is 5730, and this is enough information to find K. Of course, we're not going to be able to find the initial amount because that's not given, and that varies depending on the situation. At the rate, we know what it is for the carbon-14, and that's given by the half-life. Anyways, we know that if we plug in the half-life, this is going to give us 1/2 whatever the original amount was. So that means 5730, right? So let's see, no, Q of 5730 equals 1/2 the original amount. So this would be Q0 e to a negative KT equals 1/2 Q0. We don't need to know the initial amount because it's gone anyways. So we have e to a negative KT is equal to 1/2. So from here we get minus KT is ln of 1/2. So K is going to be minus ln of 1/2 over T. Remember ln of 1/2, so we can bring the minus in. So this is going to be ln of 1/2 to the negative 1 over T using the properties. So this is just ln of 2 over T. So, you know, their K is a positive version of our K. So, I mean, in this example, because they put the minus, that's why we're getting a positive K, because the minus is already there. Okay. All right. So we have K, and let's see, this T here should be 5730. This is 5730. So this right here is 5730. All this, we know T is 5730. So that's the exact value. If we want to approximate, what would this be? ln of 2 divided by 5730. So let's see, that would be 0.000. I'm gonna write 1 to 1. Okay, so Q of T is gonna be equal to the initial amount, which is not clear what it is, e to the negative ln of 2 over 5730 times T. And an approximation of the model would be Q0 e to the negative 0.000121 T. And this model is for carbon-14, okay? So for the substance. So any problem that deals with carbon-14 will be using this model that we came up with. Okay? As long as you assume that the half-life is 5,730 years. Okay, so the point is that if you know the half-life of a substance, you have to be able to figure out the corresponding exponential decay model. That's what this exercise was about. Given the half-life, how to find the model. Do you understand how we did this? Do you understand how we found this model? Okay. So now let's see. Let's try to answer part B. Okay. So let's see this one. Let me just fix this a little bit because it looks. So this is 5730 times K. Negative 5730 times K. Okay. All right. So let's take a look at part B. It says an archaeologist. So this is the carbon dating part. So an archaeologist uncovers human remains at an ancient Roman burial site. Okay, can anybody tell me how to pronounce this word? This is burial. I don't know. Can someone pronounce this word, please? I just wanna Here, how to say? How do you pronounce this word?
A burial, I think, like a burial site.
Burial. Burial. Okay. Okay. All right. So an archaeologist uncovers human remains at an ancient Roman burial site and finds that 76.6%. Thank you. So and finds that 76.6% of the carbon-14 still remains in the bone. Okay. How old is the bone? Round to the nearest 100 years. So what's going on here? There is an archaeologist, and then he finds some bones, right? And then he sees that 76.6% of the carbon-14 is still there on the bone. So apparently, there are equipment that tells you this, how much carbon-14 is left. And so the question is, from this information, let us try to figure out how old is the bone. And this way, you can kind of guess when was that this human was alive. Okay, when was the last time that it was alive? Because the idea is that when you die, then the body does not ingest or produce more carbon-14. Whatever carbon-14 you have, it just starts to decay slowly over time. Okay, so using this information, that's how you can tell when was the last time that it was alive. So let's try to approximate how old is the bone, and we're gonna round this to the nearest 100 years. Do you guys understand the problem? Do you understand what the problem is saying? Right, so let's do this. Decaying. So, okay, the carbon-14 doesn't die, but it decays. This is a radioactive material, so it decays. But yeah, you can, if you want, you can say it's dying. It's just going away. Okay, remember, it's not really disappearing, right? It's turning into something else, whatever that something else is. Okay, so let's see. An archaeologist uncovers human remains at a site and find that 76.6% of carbon-14 remains. So for this type of problems, it's very good to do a timeline, okay, to really understand what's going on. So what do I mean? Okay, the organism was alive at a certain point, okay? So when it was last alive and then it died, so this is the time the organism died. So organism, I guess in this case the human, but let's say organism. The time that the organism died, and then some time passed. So this is the moment that it died, and then a time passed, and then you discover the remains, okay? So remains discovered, right? And then, of course, what we are trying to figure out is how long is this, right? This time t, this is what we like, this is what we want to figure out. Does everybody understand this? The organism died at some point, a certain time passed, and then the remains were discovered. We want to know this period of time. How long was it, more or less? Do you understand this setup so far? Okay, so now let's see. And that means, let's see, when they find the remains, how much of carbon-14 do we have left? We have 76.6% of carbon-14 left, right? So that means at this point in time, so this will be our t equals to 0. We're gonna start counting when the organism died, and then we want to know how many years have passed until it was discovered. So at this point in time, this t that we need, okay, the amount of carbon-14 at this point in time that we want, I'm gonna call this t prime, okay? So which is the one that we're looking for. So this right here is t equals t prime, and we want to know that. So q of t prime, what is this equal to? This is equal to whatever the initial amount of carbon-14 was, times 76.6 because there were 76.6% carbon left, right? So 76.6% carbon 14 left. So that means that the amount of carbon 14 is going to be 0.766 times whatever the initial amount was. Do you understand this? At this point in time, the amount of carbon 14 is 0.766 of the original amount. So here, remember, Q0 is original amount of carbon 14, the one that you had, that the organism had before dying. Okay, so original amount of carbon 14, original or initial amount. Let me call it initial of carbon 14, and then the time passed, and when you discover, you found that only 76.6% is left. In other words, 0.766 times whatever that initial amount was. Do you understand this? So this right here is the critical part, understanding this. The picture is just to make the understanding easier, hopefully. Tell me if you understand that. Okay, and remember, what's the purpose of the question is to figure out T prime, because this will tell you how old the bonds are, right? An approximation, you know, plus or minus maybe 80 to 100 years, because maybe, you know, it was a very old human that died with 100 years old. So the bonds, you know, is whatever number you come up with. That's only until it died. How about how long it was alive? So, but that's why, you know, we're just approximating things here. Okay. So it's not going to be something exact, but we give you an idea on what period, you know, this human was alive. Okay. Anyway, so Q of T prime equals 0.766 times Q0, and we want to figure out T prime. So let's do that. So remember that we know that Q of T equals, this is carbon 14, so we have the model, right? I'm going to actually work with the exact number, the one that we came up above. 5730T, okay? This is the exact model. So we know this, and now when we plug in T prime, this is going to be equal to 0.766 times Q0, and we know that Q of T prime is Q0 e to the negative ln of 2, or 5730 times T prime. And now we solve. So again, the initial amount is irrelevant here. We don't need it because it cancels out. So we have e to the negative ln of 2 or 5730. You can work with the, if you like, you can work with the negative 0.00121. Okay, it's just that I prefer to work with the exact value. You should always work with the exact value whenever possible. And then we solve for T prime. So we do ln of 0.766, and so we're gonna get that T prime is gonna be equal to negative 5730 times ln 0.766 divided by ln of 2. Okay, so let's see, what is this? So what do we get for T prime? So we're gonna have, let's see, what is this? 0.766, then ln of that times 5730. That's a negative number, but now since we have a minus, it nicely makes it positive, and then divided by ln of 2. Okay, so I'm getting that T prime is about 2203.66. This is what I'm getting for T prime, and then the question is asking to round to a nearest 100 years. So this would be about 2200, right? So that means that the bones are about 2,200 years old. Okay, I want to discuss one last application, which is this Newton's law of cooling. And here we have a problem that we want to discuss. So let's read the example, and then I'm gonna write down, the formulas that we need to be able to answer this question, and then we're going to go ahead and answer the question. Let's see. A cheesecake is taken out of the oven with an ideal internal temperature of 165 Fahrenheit and is placed into a 35 degrees Fahrenheit refrigerator. After 10 minutes, the cheesecake has cooled to 150 Fahrenheit. Okay? So if we must wait until the cheesecake has cooled down to 70 degrees Fahrenheit before we eat it, how long will we have to wait? When you bake something in the oven, it comes out really hot, and you have to wait a little bit for it to cool down. Maybe let it sit on top of the counter or something for a while, or in this case, it's being placed inside a refrigerator. Okay, and then the other data point that they're telling us is that after 10 minutes, you check the temperature, and it went down from 165 to 150. It's not good enough. You want it to be down to at least 70 degrees if you want to eat it. So the question is naturally, how much do we have to wait? Right? From the moment that you took it out of the oven, how long do we need to wait? We know it has to be more than 10 minutes, right? How long do we have to wait until the temperature reaches 70 degrees so that we can eat it? Okay, do you guys understand the question? You understand? Okay. So again, this is a typical scenario in which applies what we call Newton's law of cooling, which basically tells you how the temperature of a certain object changes when you place it in a surrounding medium with another temperature. For example, if you have something that's very hot and you put it in let's say in a room, or you drop in water, then whatever the surrounding medium is something super big compared to your object. So you can have something that's super, super, super hot, but if you put it, I don't know, let's say you put it in the ocean, the temperature of that object is irrelevant in regards to the temperature of the ocean. So you're not going to warm the ocean. So the ocean is going to actually cool down that object, that object that you have that's very hot. It could be as big as you want, but the ocean is big. Okay. So the idea is that over time, the temperature of that object that you have is going to go towards the temperature, let's say, of the ocean in that case. I'm using the ocean because it's something very big, right? So, the law here says that the temperature of an object tends to go towards the temperature of its surrounding medium, okay? Of course, if it was very hot, then hotter than the surrounding mediums, then you're going to get a cooling effect, because eventually your temperature is going to go down towards whatever the surrounding medium is. But if you have an object that's very cold, as you know, if you have something that's frozen and you put it out, I don't know, under the sun or something, or you leave it sitting in the counter, eventually that's going to warm up a little bit and it's going to go towards the temperature of the surrounding medium. Okay, so this is really called Newton's law of cooling. But sometimes you have cooling, sometimes you will have warming. Okay, it depends. What's the difference between the original and the surrounding medium temperature? All right, so I'm going to give you the model that describes this behavior of either cooling or heating, depending on what's the original temperature that you have. The way you come up with this formula, you're going to learn this back when you study differential equations. Those of you that have to take differential equations, we're going to see how this model comes up to life. Okay, how do you obtain something like this? Yes, Sarah, I'm just explaining what's happening. But I'm going to be writing some stuff now, so I'm explaining so that the stuff that I write on the formula, you understand what that is. Okay? So once again, because we're going to be cooling something or maybe heating something, it really depends. There has to be two temperatures here. Okay? We have the object with its own temperature, the object that we are interested in, and then we have the surrounding medium that has a temperature that we consider that temperature to be constant. Okay? The temperature is not going to be changing. All right, so let me write it down. So this is Newton's law of cooling. But don't get deceived by the word cooling. It could be cooling or heating. It depends, once again, whether you come in with a very hot or a very cold object to the surrounding medium. Okay? All right, so we're gonna have a function. So let u of t be a function representing the temperature of a heated object as a function of time. Okay, so let's talk about heated object, but it could be also something that's very cold. It doesn't matter in this case. So let u of t be the temperature of a heated object as a function of time. In other words, initially the object is going to have a certain temperature, which could be very hot, and then this function, the job of this function is to tell you what's the temperature of the object as time goes by. Okay, so we have this, then this object, of course, it has to be placed somewhere. I mean, this object is not out of, it's not placed in a vacuum. This is being placed somewhere, so there is a surrounding medium. There are other quantities that we need to take into account. What Newton's law of cooling says is that then this formula, u of t, is actually given as follows. It's going to be equal to capital T plus u0 minus capital T times e to the kt. But in this case, k is a negative number, okay? And let me explain what each of these things are. So where capital T stands for the temperature of the surrounding medium, and this is considered to be constant. So capital T is a constant temperature of the surrounding medium. So for example, if you put it on the counter, that would be the temperature of the room. Okay, if you, let's say you heat a pizza and you take it out of the oven and you put it on top of a counter, that's your medium, the room, where the counter is, and then the temperature of the room is assumed to be constant, whatever that is. Okay, then here u sub 0, what is this? This is the initial temperature of the heated object. So as a value of the function u of t, when t is equal to 0. So this is the initial temperature of the heated object. And then here, of course, k is a constant. Here, k is a constant, which in some places, you may say it being referred to as the cooling or the heating rate. In this case, we're talking about cooling because we have something that has been heated. So this is like cooling rate. Okay, which in this case is a negative constant, negative number. And let's make sure that this that this model makes sense. So what happens as t goes to infinity? So what will be the end behavior of this function? So as t approaches infinity, what does common sense tells us? In other words, as time pass by, as time grows bigger, bigger, and bigger after you heated the object initially, and then you let it sit in a surrounding medium, what do we expect the temperature of the object to go towards to? So what would be the end behavior of this function? As t approaches infinity, what are we expecting the temperature of the object to get close to? Anybody? Let's see. Do you think that makes sense, Giovanni? Imagine that you have a pizza and you heated that pizza to 500 degrees, right? Okay. Wait a minute. Think about this. Let's use common sense first. Then we analyze the formula. You have a pizza. You heat it to 500 degrees. You take it out of the oven. It's very hot, and you put it in the room. If you let it there for 3 days and then you come back, with the temperature of the pizza is 0, will it be negative infinity? So would the pizza be frozen? No, right? It's going to be the room temperature. Whatever temperature you had in the room, eventually, the temperature of your object is going to go towards that. Very good, Giovanni. Does everybody understand this? So I don't know. Imagine that you have a metal, a ball of metal, and you hit it really, really, really hot. Like it comes out red. You hit it a lot, and then you drop it into the ocean, into a tank of water. Let's say the ocean because it's big. Because the tank actually may get hot. It depends how big is your metal ball. But if you hit it really hard and you put it into the ocean, what's going to happen? Do you think that you're going to warm the entire ocean? It's not going to warm the entire ocean, right? So eventually, as time goes by, what's going to happen to this very hot metal ball? It's going to cool down and it's going to go towards whatever temperature the ocean has. Does everybody understand this? So Maria, the point is that no, it's not going to go lower. I mean, what's making it cool down lower than if nothing else happens to the object, how can it go below room temperature? Right, if you have something that is already very hot, nothing else, there is nothing else acting on it, you let it sit on the surrounding medium, what should happen is that eventually as time goes by, it starts cooling down towards the room temperature. Okay? It's not going to get below because you don't have anything extra cooling the object other than the surrounding medium. So what makes sense is that as lowercase t approaches infinity, the temperature of the object should approach capital T, which is the constant temperature of the surrounding medium. And notice that the formula actually is taking this into account, right? Remember that K is negative, so if we look at the formula, this right here is a constant, this parenthesis, so that's irrelevant because U0 is initial temperature, capital T is a constant, so let us not worry about that. And let's look at this term then. This is the one that has little t. When t approaches infinity, remember that K is a negative number. So what do we know about e to the negative kt, or to a negative power? What happens when the argument of the exponential function approaches negative infinity? Because k is negative, t approaches positive infinity, so kt will approach negative infinity. I mean, broke it down here a little bit. This means then that kt will approach negative infinity. Remember, k is a negative number. So when that happens, what can we say about e to the kt? In other words, what happens when the argument of the exponential function approaches negative infinity? Remember the function e to the x. And this is t and this is y, and this is e to the t. That's how the exponential function looks like, right? Base bigger than 1 is increasing. What happens when the argument approaches negative infinity? What happens to it? So when the input to exponential function approaches negative infinity, it goes towards 0, right? So this term is going to go towards 0. So when t approaches infinity, what happens to this part right here? That one becomes very small, right? It goes towards 0 because the e to the kt goes to 0, and then we are left with the room temperature, which is capital T. That's the reason why we have this plus t here, just to make sure that when little t is very big, that term that we wrote with the exponential becomes very close to 0, and therefore our function is going to get closer and closer to capital T. Okay? That will be a horizontal asymptote for a graph. Anyways, that's just to understand what's going on with this formula. But basically, the model, the way it's going to look like for u of t is going to be the following. Here is t. Let you probably write t and u, not x and y. So here's t, here is u. So then let's say here we have the room temperature, let's call it capital T. So this is going to be a horizontal asymptote of the graph of the function. Then we have our original initial temperature, let's call it u0. This is the original temperature of the heated object, and then over time, this is what's going to happen. So this is how the function u of t looks like, okay? So it's decreasing, start cooling down, and then as t approaches infinity, it gets closer and closer to the room temperature. Okay, so that's the visual of how the model will look like. Okay, anyways, that's Newton's law of cooling. So let's go ahead and let's use it for the example. So once again, once you read a problem like this, you have to write down, to realize that you need to use Newton's law of cooling, then you write down your formula, and you just have to figure out, the different ingredients that you need. You need your initial temperature, you need your room temperature, and then you have to see if you're giving the cooling constant or not. Maybe you have to figure that out. It depends. Okay, so let's see. Let's try to answer the question. The solution to the problem. So remember, in the problem, what we have, the object in question is a cheesecake that it was heated to an initial temperature of 165 Fahrenheit, and then it was placed in the refrigerator to be cooled down. So the object in question is a cheesecake. So we're gonna let U of t tell us the temperature of the cheesecake. So let's say it will be the temperature of the cheesecake. Now, question: should we consider time in terms of what? Minutes, hours, seconds, years? What should t represent for us now? If we look at the problem, so what's the unit of time that we're using here? We should be using minutes. Very good. So U of t is the temperature of the cheesecake t minutes after, so 2 minutes after being placed into the refrigerator, right? After being placed into the refrigerator. Because remember, we took it out of the oven and it was immediately placed into the refrigerator. Okay, that's what the problem is telling us. Take it out of the oven and place it into the refrigerator. So that's what U of t represents, temperature after t minutes. Okay, so let's see. That means that because this is being cooled down, then we immediately can write down the formula, right? So that means that U of t is going to be equal to capital T plus U0 minus capital T times e to the kt, where, let's see, what would be capital T in this case? You can tell me what's capital T? Read the problem. So we need to take into account the medium. So what's the surrounding medium in this case? Very good, honey. So it's a refrigerator. So the capital T is going to be equal to 35 degrees Fahrenheit. So this is 35. Good. Then what is U0? So remember, what does U0 stand for? That's the temperature of the initial temperature of the object. So what's the initial temperature of the object? In this case, the cheesecake is 165. Good. So that's 165 degrees Fahrenheit. So that's U0, 165. And then notice that in the problem, we are not being told K. We don't know the cooling rate, but we are being told another piece of information. That's in the second sentence. So what's the second sentence telling us? So how do we use the information here in the second sentence? Very good. It means that if we equals 10, this is 150. Very good. So in the second sentence, the other information that we have is that U of 10 equals 150. Now with this, we should be able to answer the problem. So the question that we are asking is, how long do we need to wait until it reaches 70 degrees, right? So really the question is, find little t so that U of t equals 70 degrees, right? So we just want to know what t do we need to plug in to be able to get 70 as an output for this function. So if I understand this, okay. So it should be clear that to answer this question, the first thing that we should do is we need to figure out this k, right? Because once we know k, then we can just make the equation equal to 70 and then solve for t. So first we need to find k. So let's write down what we have so far. So far we have that u of t is going to be equal to 35 plus 165 minus 35 times e to the kt, or more nicely, so 165. So 165 minus 35 is 30. So far, this is what we know about the model, okay? And what we know also is that k is negative because we have cooling, okay? So we have a cooling effect here, so we know that k is negative. We need to find k. So to find k, we're going to use, of course, this data point, the fact that if you plug in 10, you get 150. So that means when t is 10, u is 150, and then we can figure out k. So u of 10 equals 150. So on one hand, u of 10 is going to be 35, 130 to the 10k, and this must be equal to 150. And now we can use this to solve for k. Right, let's see. So that means that 130 e to the 10k is going to be equal to 150 minus 35, that's 115. And e to the 10k is 115 divided by 130. Simplify this a little bit more. Let's see, divided by 5. So this is 23. And 130 divided by 5, that's a 26. So this is 23 over 26. So we get that 10k is going to be ln of 23 over 26. So finally, we get that k equals ln of 23 over 26 divided by 10. Now, I strongly encourage you to use the exact value because remember, the question is not about k. The question is about finding the time. So if you approximate here the value of k and you put it into the model, then you're introducing already an error. Okay? So I strongly encourage you to use the exact number of k to be able to do the next step. Okay, so now we have k, then let's update the model. So let's see questions about how I found k before I continue. Any questions on k? All right. So now we're gonna update the model. So u of t then looks like this. It's gonna be 35 plus 130 times e. Predicted that. So move this down. So e to the kt, but remember now k is this big number. So not big number, but this big expression. Ln of 23 over 26 divided by 10. All of that times t. Okay? We're gonna play with these a little bit later on, just to show you how to get rid of that ln if you don't like it. I'm gonna show you how to do that. That's a skill that you will also need for calculus. Anyways, let's just leave it like this right now. And this is the model for u of t. And so now we are ready to ask the question. So what do we want now? We want to find t so that u of t equals 70. So let's solve the equation. So we have 35, 130 e to the ln 23 over 26 over 10t equals 70. Let's see, I'm gonna do this a little bit more quicker now. So we have this number. So it's gonna be equal to 70 minus 35. That's 35 divided by 130. You can simplify. So divide this by 5, that's a 7. Divide 130 by 5, so 26. So we're gonna have ln of 23 over 26 divided by 10t equals ln of 7 over 26. So t is going to be 10 times ln of 7 over 26 divided by this quantity. Okay, so this is the exact value of t. Now all we have to do is plug in this into a calculator and calculate. Okay, so let's see. I'm gonna go ahead and first calculate the value of k. It doesn't matter, just calculate this. 7 divided by 26 ln n. Notice at the top is gonna be a negative number, but also the bottom will be a negative number because the argument is less than 1. So that makes time positive. So this is something else. If you're doing these calculations and you get a negative number at the end, something's wrong. Remember, time has to be positive. Okay? So you have to make sure that everything that you're doing makes sense. Okay, so now I'm gonna do 23 over 26. Ln of that. That's negative, that's good. So then multiply with the top after I flip it. Okay, so I get that this is about 107.03. Okay, so what does this mean? So remember, this is in minutes. Okay, so what do we need to weigh? So we need to weigh, you know, a little bit less under 2 hours, but almost 2 hours, right? So we have to weigh 1 hour and 47 minutes if you want to eat the cheesecake. So t is about 107.03 minutes. Okay, questions on these calculations? To make it more realistic, we say, so we have to wait about 1 hour and 47 minutes until the cheesecake has reached 70 degrees, and then you can go ahead and eat. But again, if you do this and you get a negative number, then something is wrong. Yes, of course. I mean, there is no way. Of course, you have to calculate. How are you gonna calculate this number? For this last part, you use your calculator. And notice how I actually use a calculator at the end. The problem is that if you use your calculator here to come up with your k, that's okay, but it's just that then you're introducing an error there. Because we have to round that k. And then, because we're using this to do another calculation, then you're going to be carrying over that error. So if you don't want to have the wrong answer, if you don't want to be off by a decimal place or two, you should put enough decimal places in your in-between calculation. So if you don't like to carry that ln down, you should probably leave like 4 or 5 decimal places when you round, and then you can work with that rounded version. And make sure that you use enough. You give yourself enough room to account for the error. Here is what I mean. If you do k, 23 divided by 26, ln, and divide that by 10. So you could say then that k is about, let's say, negative 0.01. I'm gonna give myself to here. You know, if you want, instead of carrying out that exact value of k, you may want to work with this approximation. Okay, if you want to be safe, you can throw in an extra more digit, and then instead of that, you can just work with that number around. Okay, but keep in mind that right here we introduce an approximation, so right here we are introducing an error. Okay. So hopefully after you start calculating, the error is after the decimal place as you go on. So if you are only interested in the first couple of decimal places, it should be fine down the line. But to avoid this, that's why I always prefer to use the exact answer until the end, and then you round at the end. In many places you will see people rounding in between, but then you just have to give yourself enough decimal places. So for example, with this rounded version, how would the problem look like? That decimal would be this coefficient that we have here. So all we will have to do is divide ln of 7 over 26 by that decimal. If you do that, let's see, what do we obtain? It will be 7 over 26 to ln, and then we divide by 0.0122602 negative, and I get 107.03 when you round, 0.028. So at the end, the rounding comes out to be the same. So that way, you could save yourself some time plugging your calculator later, but it's up to you. Okay, anyways, I think this was enough. Do you guys have any questions about this? Okay, so let me just show you quickly how we can rewrite that formula without having the ln. So remark, write u of t without the ln. Okay, so how can we do this? If we do that, then the formula will look cleaner. It's just that it's easier to leave with ln for calculation purposes because of the calculator that we have ln, but we don't have another base. But anyways, let's take a look at how can we get rid of the ln. So we have 35 plus 130 e to the ln 23 over 26. All of this over 10 times t. So if we want to get rid of the ln, here is what we can do. We need to use, of course, the properties of exponentials, okay? And together with logarithms. That's what I want to show you. So first of all, we can actually split this as follows. Notice that ln of 23 over 26 divided by 10, we can write that as ln of 23 over 26. I'm going to actually write it like this, to the 10, the t over 10. So to understand what's going on, so remember that whenever you have the exponential of an exponential, you multiply the exponents, okay? So if you take this guy and you multiply it with t over 10, then you're going to get exactly this exponential that we have here. Does everybody see this? You guys see this? If you multiply those two numbers, we get that. And now, why is it helpful to do this? Because now we have e to the ln of something. Remember, exponentials and ln, they cancel each other out. So we get 35 plus 130 times. The e and the ln, they cancel out, so we get 23 over 26 to the 10 over, to the t over 10. And this is again the exact model, but now this time we got rid of the ln. So this one looks cleaner than the original, at least smaller. If you are willing to sacrifice yourself accuracy and you want to round the model a little bit, you can actually write this a little bit nicer. So I'm gonna go ahead and do that. This way, we practice how to use these properties. So we can further rewrite this as 23 over 26 to the 1 over 10, and then to the t power. And then let's go ahead and let's approximate that base. 23 divided by 26 to the power of 1 over 10, which is 0.1. Okay, so we can say that this is about 35 plus 130 times 0.9878. Let's see, we're going to use 4 decimal places to the t. The big formula that we have there is approximated the same as this one. So it can be approximated by this expression. And maybe if you are okay with losing a couple of decimal places or two, like you just want to eat the cheesecake, so whether you wait 1 minute more or not is not really important. You already waited an hour and 40 something minutes. If you wait 48 instead of 47 minutes, that's okay. And this probably is a more friendly formula to look at than the original one that we have. And you can get that by just playing with the properties that we have discussed for exponentials and logarithms.